Let's work through two more examples of partial fraction decomposition. Take a look at example 5. We have the integral of 3x to the fourth plus 8x squared plus 3 divided by x times x squared plus 1 quantity squared. First thing we want to do is double check that the degree of the numerator is less than the degree of the denominator. At first, it might not look like it. But if you think of expanding out this x squared plus 1, we would have an x squared times x squared, which would be x to the fourth. Multiply the x to the fourth by this x. The denominator actually has a degree of x to the fifth. So the degree of the denominator is greater than the degree of the numerator, so we can proceed with partial fraction decomposition. The next step would be to factor the denominator. This denominator is already completely factored. X squared plus 1 is an irreducible quadratic. So we're ready to write out the form for the partial fraction decomposition. 3x to the fourth plus 8x squared plus 3 divided by x times x squared plus 1 squared. Each of these factors will give me a fraction in the decomposition. The first one's linear, so I write a divided by x. For the next factor, I have a repeated quadratic factor. This will give me two fractions. The first one has a denominator of x squared plus 1. The second one has a denominator of x squared plus 1 quantity squared. In both of these numerators, I have linears, bx plus c and dx plus e. I want to solve for these constants now. So I multiply both sides of the equation by x times x squared plus 1 squared, and I distribute this through and try to simplify. On the left-hand side, the denominators always cancel, and we just have the numerator. On the other side, when I distribute to the first expression, the x's will cancel, and I will have a times x squared plus 1 squared. For the second fraction, when I distribute, one of the x squared plus 1 terms cancels. So I'm left with bx plus c times x squared plus 1. For the last fraction, when I distribute, the x squared plus 1 squareds cancel. And I'm left with dx plus e times x. At this point, I need to expand out this expression. This is rather tedious algebra, so we'll just try to stick with it, and then we'll solve for these values of the constants a, b, c, etc. So I'm just going to make myself a little bit more space here. I have to FOIL out x squared plus 1 squared. That's x to the fourth plus 2x squared plus 1. And then I need to expand out this expression here. First, I'm just going to think of foiling these two binomials, and I'll keep the x out front. So I'll have plus x times, and I'm just going to FOIL out these expressions here. bx times x squared is a bx cubed, and then I'll have c times x squared, so cx squared, plus bx plus c. All right, for the last term, I have dx times x, dx squared, plus ex. I still need to simplify. I want to group like terms after this, and then I'll be able to solve for the a, b, and c. All right, I can distribute the a. So ax to the fourth plus 2ax squared plus a, plus, now I need to distribute the x into all of these terms. So bx to the fourth plus cx cubed plus bx squared plus cx plus dx squared plus ex. This is alphabet soup. It's rather tedious, so we'll try to get to the end and solve for these constants, but at this point, we need to really watch our algebra to make sure we don't make mistakes here. All right, I need to group like terms according to the x's. And what I like to do is to put a little dot over each term after I've dealt with it. So I see x to the fourth. There's an ax to the fourth and a bx to the fourth. So I'm going to first group those together. Those are both x to the fourth. There's an a and there's a b times x to the fourth. Now I look for x cubed. I see cx cubed. All right, so there's only one of those. plus cx cubed. Now I look for x squared. I see a 2ax squared, bx squared, dx squared. So for the x squared, I see 2ax squared, bx squared, dx squared. So I have 2a plus b plus d in these parentheses. Now I look for multiples of just x. For multiples of x, I have cx and ex. So a c plus e times x. Finally, I look for any constants. There's only one constant, which is the a. So I write that at the very end. There we are. Now, all of this equals 3x to the fourth plus 8x squared plus 3. I want to group the corresponding terms together. So I look for the x to the fourth terms. 3x to the fourth equals a plus b x to the fourth. So 3 equals a plus b. Now I look for degree 3. I have cx cubed. There's no x cubed on the other side. So really there's a 0x cubed. This tells me that c equals 0. Now I find the x squared terms. I have 2a plus b plus d equals 8. And then for linear terms, multiples of x, I have c plus e times x, but there's no multiple of x on the other side. There's a 0x. So c plus e has to equal 0. All right, and finally, the constant terms have to match up. So I have a constant term of 3 over here, constant term of a over there. That tells me that a must equal 3. Now, I need to solve for the a, b, and c. And for these numbers, they work out rather nicely. In general, we could have rather difficult equations that we would need to solve, but for our examples, they will all be fairly straightforward. I have a equals 3, and using the first equation, if a equals 3, then b must be 0. So I'll write b equals 0. Now, from the second equation, I know that c equals 0. And using this 2a plus b plus d expression, I know what a and b are. So I plug in a 3 for a, 0 for b. So 2 times 3 plus 0 plus d equals 8. 6 plus d equals 8. That tells me that d must be 2. All right, and in the final equation, we have c plus e equals 0. We already know that c equals 0. So 0 plus e equals 0. That tells me that e is 0. And there we have it. We have all of the values of the constants a, b, c, and d. Most of them were actually 0, but a equals 3 and d equals 2. Now we take those values and we put them into the form of the partial fraction decomposition. So far we've only done algebra here. We have not done any calculus. But now that we've solved for these constants, we can put them into the form of the decomposition. A equals 3. B is 0, C is 0, so this second fraction actually goes away. D equals 2, and E is 0. So the partial fraction decomposition for this rational function is 3 over x. The second fraction goes away because the numerator is 0. And then in the next, I have 2x divided by x squared plus 1 squared. All of this work to get the partial fraction decomposition of the original rational function. Now that we've decomposed into smaller partial fractions, we can find the antiderivatives. For the first fraction, we have 3 times the natural log of the absolute value of x. For the second fraction, we could solve this using u substitution. We would choose u to be the denominator, but I think this is one that we want to be able to recognize u substitution without having to work through all the steps. So the derivative of x squared is 2x. That's what's sitting in the numerator. I'm really taking the antiderivative of something raised to the negative 2 power. You could double check this answer on your own. I encourage you to do that. But we will get negative 1 divided by x squared plus 1. We add a plus c, and that is our answer. If you take the derivative of this expression and then add the fractions together and simplify, you will obtain the original rational function. Finally, let's take a look at example 6. My first step will be to double check that the degree of the denominator is greater than the numerator, which it is. So next I want to factor the denominator. I can factor an x squared from both those terms, so that's what I'm going to do first. I'll copy down the numerator and then factor the denominator at x squared times x squared plus 5. I have a repeated linear factor of x squared, and the x squared plus 5 is an irreducible quadratic. If we check the discriminant, I have 1 x squared plus 0x plus 5. So if we check b squared minus 4ac, we would have 0 squared minus 4 times 5. We have a negative discriminant, so this x squared plus 5 is irreducible quadratic. Now let's write the form of the decomposition. For the repeated linear factor, I get two fractions, a divided by x plus b divided by x squared. Notice, even though I have an x squared in the denominator, because it's a repeated linear, I still only have a single constant in the numerator. I do not have bx plus c. The x squared is a repeated linear. All right, then we have this irreducible quadratic, x squared plus 5, and this needs a numerator of the form cx plus d. Now solve for a, b, and c, and d. Multiply everything by the denominator, and now expand everything out, group like terms, and solve. When I distribute to the first fraction, one of the x's will cancel, and I'll be left with a times x squared plus 5. When I distribute to the second fraction, the x squareds cancel, and I'm left with b times x squared plus 5. When I distribute to the last fraction, the x squared plus 5's cancel, and I'm left with cx plus d times x squared. Now we want to expand everything out and group like terms. Ax times x squared, ax cubed, plus 5ax, plus bx squared, plus 5b, plus cx cubed, plus dx squared. I group according to powers of x. So I first look for x cubed. I have an ax cubed, cx cubed. I want to group those together. Since it's a and cx cubed, I will write a plus c x cubed. Now I look for x squared. There's a bx squared and dx squared. I'll group those together. b plus d x squared. Now look for single multiples of x. 5ax, looks like that's the only one. 5ax, and then there's only one constant term, which is the 5b. All of this is equal to the 4x cubed plus 6x squared plus 10x plus 15. So we're going to get 4 different equations with all these constants, and then we'll solve for the a, b, and c. The x cubed coefficients have to be equal. So a plus c must equal 4. The x squared coefficients have to be equal. So b plus d equals 6. Same with the linear factors, 5a equals 10. And last but not least, the constant 5b has to equal 15. All right, well, I can solve this last one. Divide both sides by 5, we get b equals 3. I can solve the a equation. Divide both sides by 5, and I get a equals 2. All right, if a equals 2, I can use that for the first equation, and I put in a 2 for a. 2 plus c equals 4. This tells me that c must equal 2. And then finally, b plus d equals 6. but I know that b equals 3, so d must also be 3. If b equals 3, I need d to also be 3. That gives me the last constant. So here I have a, b, c, and d all solved. Once I have these, I put them into the decomposition form, and then I try to integrate. So this rational function decomposes as 2 divided by x plus b, which is 3 divided by x squared, plus cx plus d, 2x plus 3, divided by x squared plus 5 dx. We have successfully worked through the algebra, and we are now ready to integrate. Taking antiderivatives of the first fraction, we have 2 times the natural log of the absolute value of x. For the next one, it's tempting to use the natural log rule again, but I can only use the natural log rule when I have x to the first in the denominator. This is 3 divided by x squared. So if I think of this as 3 times x to the negative 2, I would increase the power by 1. 3x to the negative 2 plus 1 is negative 1. Divide by the new power of negative 1. That is the correct antiderivative of 3 over x squared. How about this last fraction? How do we deal with that? Well, my first step is going to be to split it into 2 separate fractions. I can split this at the plus sign in the numerator. So I have the integral of 2x divided by x squared plus 5 plus the integral of 3 divided by x squared plus 5. This integral we might recognize as a u substitution. We choose u to be the denominator here. The derivative of x squared is 2x, so this will work out nicely. But what about this integral here? We have 3 divided by x squared plus 5. It might look tempting to use a u substitution again, but u substitution will not work here. To solve this last integral, we need the special arctangent identity that we wrote on the front page of the handout. Here it is again. If we have the antiderivative of 1 over x squared plus a squared, this is 1 over a times the arctangent of x over a. All right, so let's continue on. We have 2 natural log of the absolute value of x minus, I can write this as 3 over x if I simplify that a little bit. Taking antiderivatives of this rational function, this would be u substitution. I'm going to skip over the steps, but I encourage you to make sure that you know how to do this. This is natural log of the absolute value x squared plus 5. Think about taking derivatives, and we'll see that we get back to the original rational function there. Now for this last integral, I'm going to take out a 3, and then the denominator isn't quite in the form. I want to have an a squared, and I have 5. So instead of writing 5, I will write square root of 5 squared. X squared plus square root of 5 squared dx. Now my fraction has the form that I'm looking for, x squared plus a squared. Here, the a is square root of 5. So now I can use this arctangent identity. So the final answer, copy down all of this stuff. We have 3 times, now we use the arctangent identity with a equal to square root of 5. 1 over the square root of 5 times the arctangent of x divided by the square root of 5. We add plus c at the very end, and that is the answer. If we were to take the derivative of this expression, we would get a bunch of rational functions that we could then add together using common denominators and get back to the original integrand.